This week, we're going to tell you about one of the great success stories of mechanism design, the Vickrey-Clark-Groves mechanism. And in this video, I'm going to give you a high-level taste of what this mechanism does and why it's important. So what is the Vickrey-Clark-Groves mechanism for? Essentially, it solves a problem that we encounter in mechanism design pretty often, where I, as the designer, am interested in implementing an efficient outcome. What that means is I've got a set of self-interested agents, each of whom has private information about how much they value each of the different things that could happen in the world. And what I'm desiring to do is always to pick the thing that maximizes the sum of the ways that the agents actually feel about these different things, which of course is something that I, as the designer, don't know. So what I need is for the agents to tell me how much they value different things, and I want then to pick the thing that maximizes the sum of their values. This would all be fine, except that of course the agents could lie to me about how much they value different things. So what I want to do in a transferable utility setting here is to impose a set of payments that make it the right thing for the agents to tell me the truth, so that I can then solve the pretty simple problem of maximizing the sum of how they feel about the different things. The trick is to set up these payments in the right way, so that the agents really will want to tell me the truth. The great success of the VCG mechanism is that telling the truth for the agents is a dominant strategy. So it's a really strong kind of implementation. The agents really will want to tell me the truth, and they don't even have to think about what the other agents will do. It's simply the right thing for every agent to tell me the truth about their own valuation, and then if I run the VCG mechanism, the payments will be such that the agents will feel like they've done the right thing by just telling me the truth. I'm going to show you a number of different examples that gives you a sense of what this means in practice and why it's exciting. Let's start with the simplest example, where I'm going to allocate a single thing among a set of agents. So imagine a government that wants to privatize a public utility like a power plant. Now, when a government wants to privatize something, it's not usually because it just wants to collect a bunch of money, but instead it's that the government thinks that this public utility could be more efficiently operated by somebody in the private sector than by the government. If this is the case, the government typically wants to figure out which among a set of potential buyers values the utility the most, because that's the buyer that would then most efficiently operate the utility afterwards. So you could sort of think the government could go to each of these potential buyers and ask them, how much do you value the power plant? And it could then just give the power plant to the utility that values it the most. The problem, of course, is that if it just did this, the buyers would lie. They would all claim very, very high values in the hopes of being the highest, and the government would probably not end up giving the power plant to the right company. So instead, the government has to sell the power plant, even if it doesn't care about collecting the money. The question then is, what rules should it use for imposing payments on the different potential buyers? And if we were to use the VCG mechanism here, this would give us a way of imposing payments on the different buyers so that we would ensure that each of the buyers would simply tell the government the truth about how much the power plant is worth to them. This is a simple example because here the outcome space is just giving the power plant to each of the potential buyers, and we're just allocating a single good, essentially the power plant here. But VCG also works in other settings that look pretty different from this. Let me give you an example of that. Let's imagine here the simplest possible outcome space. There are just two things that could happen. I have a set of businesses on two sides of a river, and the two outcomes are that a bridge could be built or could not be built. And what I want to do here is to build the bridge if the sum of values that the agents have for the bridge exceeds the cost of its construction, and not build the bridge otherwise. And again, what I want to do here is collect information from all the businesses that has them tell me how much it's worth to them to have the bridge be constructed. And it may well be that they have a negative value for the bridge being constructed because maybe they're better off in the world where there's no bridge. So I want to look at all of this aggregate information, and I want then to figure out payments where I might compensate some businesses that are hurt by the construction of the bridge I might charge some businesses that are benefited by the cost of the bridge, and eventually collect enough money that I can actually pay the construction workers who, of course, have a negative value for the bridge being constructed because they have to do work, and overall decide whether the bridge, in fact, should be built or not. So again, the VCG mechanism would just do the right thing here. It would come up with payments that work out in the right way, as we'll see when we do this example a bit more formally later. Here's a third example, which is, again, pretty different from the first two. It's a little bit more like the bridge example. I need to make kind of a social choice here rather than allocating one thing among different people. Here, the problem is scheduling meetings. So imagine that you're in a problem which I really face in my life all the time, where it's necessary to schedule meetings between people who have different values for different times in their calendar, and who may not tell you the truth about whether they're available or not. So, for example, they may lie to you and tell you, I'm busy first thing in the morning, just because they don't actually want to come in first thing in the morning. And in principle, it's fine that they have a bad value for that time, but it may be that that turns out to be the only time that everybody else is available. So it may be better to be able to reward that person strongly for coming in first thing in the morning, rather than not being able to have the meeting at all. So here what I want to do, again, now I have to do this in a setting where payments are possible. So I have to imagine either that I really am going to pay people bonuses for coming to their meetings, or I have to imagine that I have some kind of artificial currency which is still scarce, which is used for meeting scheduling and people care about. So maybe, in my case where somebody has to come in at a really undesirable time for them, they accumulate a lot of credit that they can use for something else that they value. But again, the way the VCG mechanism would work here is it would give everyone a dominant strategy for telling me all of the values they have for the different times at which meetings might happen. And it will then come up with payments that make everybody happy about having told me this and allow me to implement the social welfare maximizing meeting schedule. So let's look at one more example, which indeed we'll work through numerically in later videos in a stylized form. This is the problem of buying a path in a network. And the network I want to think about here is a railroad network from the American Midwest in 1881. So each of these red lines here corresponds to a rail link that existed in this area in 1881. And I don't know if this is actually true, but I want to claim that each of these red lines corresponds to a privately owned railroad that is owned by a different railroad operator. It certainly is the case that in the early days of railroads in the United States, there were lots of different privately owned railroads. So I want to imagine that each of these railroad links has its own private cost for what it would cost to ship something along the link. Over here is the Hocking Valley coal field, which was an area of coal production. And of course, over here is the city of Chicago. And the problem that I'm interested in is the problem of shipping a bunch of coal from the Hocking Valley coal field to Chicago. So I, as the coal company, need to buy a sequence of links in the network that would get me all the way from the coal field to Chicago. Now, if I was to use the VCG mechanism, I could solve this problem by asking each of the coal companies what their utility is for being selected to ship coal. And for each of them, this would be a negative number because it actually costs them something to do the shipping. So each of them would tell me a negative number. They would have a dominant strategy to tell me the truth about what their real cost is. I can then look at these numbers, and the social welfare maximizing outcome here is the shortest path in the network. It's the set of paths that together get me from the Hocking Valley coalfield to Chicago and imposes the least negative cost on all of the agents. Now, why would they be willing to be chosen if they're getting given, if they're in a situation that they negatively value? Well, to make this a dominant strategy, VCG in this case is going to end up paying all of the agents rather than imposing payments on them as it did, for example, in the privatization example. So in this example, it's going to figure out a way to pay the agents that makes them willing to have told me the truth and ends up buying the shortest path. So overall, what have we seen here? The VCG mechanism is an amazing way of solving all of these apparently very different problems, and indeed lots more. And it again, to remind you, the property that it has is that it chooses the efficient or social welfare maximizing outcome in a transferable utility setting in a way that gives agents dominant strategies to tell the truth. We'll spend the rest of this week telling you in more formal detail how the VCG mechanism is defined, how it works, and what its strengths and weaknesses are.
Okay, hi folks. So this is Matt again, and we are now going to talk about Vickrey-Clark-Groves mechanisms, or VCG mechanisms. And these have become one of the most well-studied set of mechanisms in game theory, and with good reason. They have wonderful properties, some very interesting properties. And let's talk a little bit about the kinds of positive results we'll get now out of these mechanisms before we go into the detailed definitions and so forth. So we're going to work in a quasi-linear setting, and we're going to work here. Remember, now we'll look at direct mechanisms where society will have a choice rule and a payment rule based on what preferences people report to the mechanism. And the nice thing about VCG mechanisms, Vickrey-Clark-Groves mechanisms, is that they will have truth as a dominant strategy. So people won't have to worry about what other individuals are doing, regardless of what their preferences are. The best thing they can do in terms of maximizing their utility is to tell the truth. And this mechanism is also going to choose efficient X's. So choices here mean when we think about which X in X maximizes the overall total sum of utilities in the society, it's going to pick those. So it's not that it might not be efficient in terms of making all the payments balance, but it's going to make efficient choices. Okay. Now these mechanisms, in terms of the history of this, Vickrey was the first to define these in an auction setting. So this is going to have a close relationship to second price auctions and basically generalizes second price auctions to a more general class of auctions known as Vickrey auctions in the auction setting. Clark then generalized that to a more general class of settings and defined what was known as the pivotal mechanism, which is a special class of these mechanisms. And then Groves gave basically the class of all such mechanisms, and there's some nice properties of a more general class of these. And so we'll look at these in more detail. The nice thing is we're going to have dominant strategies and efficient choices, and the quasi-linearity is going to be critical here in making sure everything works. And so we're looking at private values, so conditional utility independence in general, and we'll be looking at settings where we have quasi-linearity is going to make things go for us. Okay. Under some particular settings, we'll be able to get additional things like a weak budget balance condition, interim individual rationality, other kinds of nice things coming out. But more basically, the key ingredients here are going to be dominant strategies and efficiencies. Okay, so let's start with the general class of these mechanisms, which are known as Groves mechanisms, after Ted Groves. And so we're looking at direct mechanisms. So this is going to be making a choice out of whatever our X set is. And then the P's are going to be, the P is going to be in Rn again, right? So it's telling a payment for each of the individuals. And the interesting thing about a Groves mechanism is going to be any mechanism of the following sort. Look at the announced utility functions. Each person is telling us now what's their valuation function. That's their private information. So we get these announcements. So people are telling us V hat 1 through V hat n, which are telling us how do they value the different X alternatives. So society, first of all, is going to make a choice which maximizes the total sum of those. If that's unique, then that ties this thing down exactly. Sometimes there could be ties. It's going to always pick something which is best for society in terms of overall maximization. Then the key thing here is going to be the payment rule. And what's the payment rule going to look like? The payment rule for a given individual is going to be something which is going to depend on what some function of what the other individuals announced. So minus I, meaning the vector of utility functions announced by the other individuals other than I. And it's also going to have a part here, we'll subtract off the sum of the announced valuation functions evaluated at the chosen alternative by society. Okay, so society makes a choice. We look at how much does everyone else get in terms of utility for that. We can add in some other thing that doesn't depend on a given individual. So sometimes it's going to be useful to add in other things, and we'll talk about that in a moment. Anything which has this structure to it is known as a Groves mechanism. Okay, so this is a particular class of mechanisms. Sometimes these are referred to as VCG mechanisms. That name has more recently been used to look at a situation with a very specific payment rule here. And we'll talk about that in a moment. But this is a general class of Groves mechanisms. Okay, so now let's look at Vickrey-Clark-Groves mechanisms, the special class, which is also, these go by different names in different literatures. So in the economics literature, this was originally known as a pivotal mechanism. In part of the computer science literature and the game theory literature more generally, it's becoming known as VCG mechanism. Sometimes VCG is used to look at the broader class. But what's specialized here is, if you remember that H function we had, so we had an H function, hi of v hat minus I, that function now takes a very specific form, and that specific form in particular is one where what we do is pick something which maximizes the sum of everyone else's utility. So what would society choose if I were ignored, and then look at the total sum of utilities that would come out of that, and compare that to what people get when I is taken into account, right? So this is the choice that's made when I is being accounted for. This is the choice that would be made if we ignored I. And this pivotal mechanism, what it does in terms of I's payment is say, how much would everyone get if we ignored you? How much does everyone else get if we take you into account? This is generally going to be a lower number, right? This is going to have to be a lower number. People can't be made better off by including I in terms of the decision. All that can do is distort things away from the overall maximizer for these individuals. So this number is generally going to be a non-negative number. So this will be a payment that different individuals would be making into the society. Okay, so let's have a look at what we end up with here. And so we've got this structure, something which maximizes overall utility and a particular payment scheme. And so what you get paid is everyone's utility under the allocation that's actually chosen, except your own. You get that as the direct utility. And then you get charged everybody's utility. So when we take off this minus PI, what you're going to be charged is how much everyone else would have gotten in this world where they didn't have to take you into account, less what they're getting in the world where they do have to take you into account. And so we can think of this as the social cost of an individual I, right? So this is social cost of I. What does that mean? That means having I present imposes some change in utility for the other individuals. Individuals are paying their social cost. Okay. Who pays zero in this world? Well, people who end up not affecting the outcome at all. So their presence or non-presence, their announcement of their utility function didn't affect things overall. Okay. So who pays more than zero? Pivotal agents who make things worse by existing. So there's situations where the fact that they existed actually changed the outcome in a way that made the individuals worse off. Who ends up getting paid? Well, people can in some circumstances, under some of these mechanisms, gets paid by making things better off for other individuals. Okay, one nice thing about these mechanisms, and the beauty of these mechanisms, is that truth-telling is going to be a dominant strategy under any Groves mechanism, including the pivotal mechanism or these VCG mechanisms. So when we have this basic form, the theorem tells us that truth is a dominant strategy. And let's go through that. So we'll first go through this theorem, and then we'll talk about a converse theorem. It says basically, if you want truth to be a dominant strategy in these settings with quasi-linear preferences and private values, it's going to have to be a Groves mechanism. So these mechanisms will be dominant strategy, and basically in this setting, they will be the only dominant strategy mechanisms that result in efficient X choices. Okay, so let's have a look at this. So let's look at, to try and see why this theorem is true, let's think of what I's problem is. So what they're getting is this is their true utility, VI, and they're thinking about what they should announce, right? So I is choosing what function should I tell the mechanism that I have in terms of my utility function. So that's going to affect the outcome, and it's going to affect the price. And this is their overall utility, so they want to choose the announcement to maximize the utility function. So let's have a look at the Groves mechanism, substitute in for this, and then see what people's incentives are in that world. So under a Groves mechanism, your payment rule looks like this. So it looks like an HI minus the V hat, and when we take the minus of the overall thing, we end up with this. And there should be an I here, subscript I. So when we look at that payment scheme, the individual is choosing this to maximize their overall utility. So first of all, notice that this thing does not depend on V hat I. So maximizing that is equivalent to maximizing this when we ignore it. Okay. So now we've boiled this problem down to solving this problem. Okay, so maximize VI of the chosen alternative as a function of what you announce, plus the other people's announced utilities. Okay. Now one thing to notice is this begins to look like you're just trying to maximize the overall sum of utilities, where yours is the truthful and then everyone else is what the announced one is. So I would like to choose a declaration which would lead the mechanism to pick an outcome which is going to maximize this overall thing, right? So what you'd like to do is choose a V hat I that will lead the mechanism to make a choice which solves this problem. Okay, so if we go back and look at this problem, maximizing overall the V hat I is equivalent to saying, let's try and get the mechanism to choose an X, which will maximize this overall. If that declaration gets an X that which maximizes this, then that's certainly doing as well as possible. Now remember, under a Groves mechanism, the X of the V hat I is something which maximizes exactly the sum where what you've done is put in your announced utility. And if you want to get them to do it with respect to your true utility, then the way in which to do this is to have your announced utility be equal to your true utility, and then they'll be maximizing exactly the function that you want them to be maximizing. And that means that truth is a dominant strategy. Right? So the Groves mechanism will choose X in a way that solves this maximization problem precisely when V hat is equal to VI. Therefore, truth is a dominant strategy. So this is a deceivingly simple proof. So it takes a while to go back through this, convince yourself it's true. But the basic idea here is the payment that a given individual has is essentially what everyone else's announced utility function is. And whether those are truthful or not, from their perspective, what they're getting in terms of an outcome is something which then maximizes the overall total sum of utilities, because what they're doing is maximizing their true utility plus what other people have told the mechanism their utility functions look like. And by being truthful, they get an outcome which maximizes that overall total sum, which indeed is the best they can do in terms of maximizing their utility given this payment rule. So the nice thing about these VCG mechanisms, or in general the Groves mechanisms, is they align the individual's incentives with the society's incentives by making sure that the payment rule accounts for what their decision choice is, what the impact of their announcement is on everyone else's utility. Okay. Now, the uniqueness of these things in terms of being the converse theorem, there's a theorem by Green and Lafont from the late 1970s, early 80s, which then says that there's a converse here. So suppose that for any utility function, each individual could have any possible utility function over the public decision or the non-monetary decision. So domain is going to be rich in a very particular sense, that people could have any possible utility ordering of utility function over the set of alternatives. Then we'll say that a mechanism that's efficient, so it's choosing a decision as a function of the announced preferences, which maximizes the overall utility. That's going to have truthful reporting as a dominant strategy for all agents and preferences only if it's a Groves mechanism. So the payment rule has to look like what we said in terms of a Groves mechanism. That's the only way that you can be truthful for all possible announcements of preferences. So not only are the Groves mechanisms dominant strategy incentive compatible, but if we require efficient outcomes, these are the only ones that work. Okay, so I won't prove this explicitly. The proof is actually fairly straightforward. You can find a version in a survey I wrote on mechanism design on my website. But in terms of summary here so far, what have we got? Groves mechanisms and a special class of those, the pivotal mechanisms or VCG mechanisms, have really nice properties in terms of incentives. Truth is always a dominant strategy. The agent's payments rules basically align their incentives with the society in terms of making sure that they're taking into account their impact on other individuals' preferences and utilities, and therefore we end up with efficient outcome choices. So that leads people to internalize the externalities and leads to efficient choices over the X's. Now, one thing that is also important to emphasize is that it might be that these mechanisms are not overall efficient in the sense that we might have to charge the agents money in order to get this to work. So it could be that the sum of the payments, the PIs, is greater than zero. So that means that people are making a bunch of payments into the society, and we are not giving them all back to the society. So either we have to funnel them off to somebody who's not involved in any of the decision process, or we're going to have to burn that. If we try and give it back, that could change the incentives that we've just aligned so nicely. So the part of the issue about this is we've put these payment rules in which align incentives very nicely, but in order to do that, we might have to be charging agents a lot in terms of what their impact on the society is. And in order to get things to balance, we might have to give up some nice conditions that we'd want. So nice thing about these mechanisms, dominant strategies, and that's why they've been studied so extensively. There's a number of settings where they form nice benchmarks and have really a long list of nice properties. There are other settings where they serve as a benchmark and don't satisfy all the conditions we'd want, and that generally has to do with the balance kinds of conditions of the payments and the idea that sometimes people will be charged even if they would rather not participate in the mechanism. So we might want to think about individual rationality conditions, balance conditions, and other kinds of things. So we'll take a look at these in more detail and context, and that'll be our next thing up.